Hi today students, this week's topic is about systems of linear equations, more specifically how to solve them. So first of all, when we have a system of linear equations, it just means that we have two different linear equations put together to make a system. So for example, 2x plus 3y equals to 10, x minus 4y equals 3. So here I have two linear equations, both in standard form, and together they form a system. So a solution to a system of linear equations is a pair of values, x, y, that is a solution to all equations in the system. So basically, it's certain x, y values that when plugged into each of these equations will make them both true. So it's the solution to each of them. There are three methods for solving systems of linear equations: graphing, substitution, and addition-elimination. Today we're going to be going over graphing. This is not one of the ideal ways to solve a system of linear equations. Out of the three, it's the least effective, as graphing we can always be a little bit off very easily, whereas with algebraically, the two other methods, we're able to find a very precise answer, even if it's like a decimal or a fraction. When solving a system of equations, there are three possibilities. There's either one solution, no solution, where we say the system is inconsistent, or infinitely many solutions, where we say the system is dependent. We're going to be showing this in the next slide when we talk about specifically solving systems using the graphing method. So again, there's either one, none, or infinitely many. So when we're solving systems of equations by graphing, we basically just graph each of the lines and find their intersection point, because wherever they intersect, that point is a solution to both equations, solution to both lines, right? It lies on both lines, so that's the solution. When we have something with one solution, this means that it has one intersection point. So for example, we have a line there and a line there. So I can see very obviously that I have one intersection point right there where it crosses. So this intersection point will give you a coordinate. The coordinate's actually the solution, where you have a coordinate x, y. So that's one possibility. The second is when we have no solution. Basically, this is when I have two linear equations that have no intersection points. When I graph it, there's no intersection point. There's no one point, no one solution that is a solution to both of these equations. So there's no solution. This is inconsistent. From here, if you have something like this, you'll just write out no solution, inconsistent. The third possibility, infinitely many solutions or dependent, this occurs when I have two linear equations and they actually lie on top of each other. So for example, the first would be something like this, and the second one will actually lie right on top of it. Okay, so there's no gap actually. They lie right on top of each other. So for this one, it's true that every single point on each of these lines, so every single point right here is where it's true for both of them, right? So that means that there's infinitely many points on this line that are solutions. So this one, you would actually write infinitely many solutions. A lot of teachers also accept just many solutions, and you'll also say that it's dependent, okay? I like to remember in order to remember dependent, I say, okay, there's two lines and they're leaning up on each other, right? They depend on each other, they lean on each other. And so that's what you'd write. Infinitely many solutions, dependent. Now we'll go through some examples of solving systems of equations by graphing. So here I have two different equations, linear equations. Together they form a system. Sometimes you'll get it in brackets just to show very explicitly that they do form a system. So the first thing you need to do is write each of these in a form that you are able to graph. So The easiest form for us to graph, as we learned from topic 14, is the slope-intercept form. So I'll actually take each of these equations and write them in slope-intercept form and graph them. Looking at this first equation, I have 2x plus y is equal to 1. In order to put it in slope-intercept form, I'm actually just going to isolate y by moving this 2x to the other side of the equation. So I'm going to subtract 2x on both sides, which leaves me with y equals negative 2x plus 1. From here, I can easily identify my y-intercept and my slope. Y equals mx plus b, where m is the slope, b is the y-intercept. So my y-intercept is 1. My slope is negative 2. Again, with slopes, we always want to make it a fraction. The equivalent fraction to negative 2 is negative 2 over 1. So I know I'm going to be going down 2 and 1 to the right. So graphing this, I'll start with my y-intercept. I have a y-intercept at positive 1. I'm going to be going down 2, 1 to the right. So I'll go down 2, 1, 2, 1 to the right. I might actually just keep doing this a few times just to make sure that I keep my same slope. So I'll go down 2, 1 to the right, and so on. I'll just keep doing it just to complete my graph. And the same thing on the left side, I'll just go up 2, 1 to the left. Like basically, if I was to work backwards, I'm just following this line. And from there, I can actually just connect my dots. Again, if you have a ruler or a straight edge, that would make this a lot easier. This is my first equation. Graphing the other line with green, I'm actually going to manipulate it algebraically first to put it in slope-intercept form again. X minus 2y is equal to 8. I'm going to isolate y by first moving the x, and then I'll divide by negative 2. So I have negative 2y is equal to negative x plus 8. Dividing now by negative 2, I'm left everything by negative 2. I'm left with y is equal to negative over negative becomes positive, so I have 1/2 x minus 4. From here, my y-intercept is negative 4. Slope is 1/2. So I'm going to move up 1, 2 to the right. So I'm going to start down at here at negative 4. Up 1, 2 to the right. Up 1, 2 to the right. Up 1, 2 to the right. So I can already see just from putting that one first line that it's going to intersect right there. So doing this, I can see that there's one solution, and this occurs at this point right here, right? Let me just make that a little bit darker. This point right here. So my solution is going to be an xy value, and this is where x is equal to 2 and y is equal to negative 3. Looking at this next example, I'm going to graph them by working with each of them individually, putting them in slope-intercept form, and then graphing them. So looking at this first one, which I'll graph in blue, we have 2x minus y is equal to negative 2. To solve this one, to isolate y, I'll first move this 2x to the other side by subtracting it from both sides. So I'm subtracting 2x from each side, so I'm left with negative y is equal to negative 2x minus 2. From there, I need y to be completely isolated, so I'm going to actually divide everything by negative 1. And what this is going to do, it's just going to change the sign of everything else. So y is equal to negative divided by negative becomes positive 2x. Again, this becomes positive 2. From here, we can see again, my y-intercept is 2. My slope is 2, so my slope is actually going to be 2 over 1. So I'm going to move up 2, 1 to the right. Up 2, 1 to the right. Up 2, 1 to the right. Okay. So I have this. I'm just going to copy the same pattern all throughout. Okay, it's a little bit off, but you get the gist of it. Okay, graphing this next one again with green. 2x minus y is equal to 3. Subtract 2x from both sides. I have negative y is equal to negative 2x plus 3. Dividing everything by negative 1, I'll be left with y equals 2x minus 3. Where my y-intercept is negative 3 and my slope is 2, making that a fraction. I'll make it 2 over 1, which means I'm going to go up 2 again and 1 to the right. So starting at negative 3, up 2, right 1, up 2, right 1, all the way across, and then I will do this. Looking at these lines, there's obviously no intersection points, and because they have the same slope and they don't lie on top of each other, there's going to be no intersection points anywhere along these lines. So for this one, I'll actually record my answer as no solution. And you must also put that it is inconsistent. This last example for graphing, I'll do the same thing again. In blue, working with this first one, 6x plus 3y is equal to 12. I'll subtract 6x from both sides. So I'm left with 3y is equal to negative 6x plus 12. Dividing everything by 3, I'm left with y is equal to negative 2x plus 4. Y-intercept 4. Slope is negative 2 over 1. So I'm going to go down 2, 1 to the right. Okay. Working with the other equation, 2x plus y is equal to 4. Subtract 2x from both sides. Y is equal to negative 2x plus 4. Already I can see that these two are exactly the same, right? Same y-intercept, positive 4, same slope, negative 2. So obviously these two lines are going to lie on top of each other. As we discussed earlier, this is when we have infinitely many solutions. So our answer is going to be infinitely many solutions. And we can say that this system is dependent. So that's it for part 1 of topic 15, which is to solve system of equations by graphing.